The amount N of a monoatomic gas at an initial temperature T0 is enclosed in a cylindrical vessel fitted with a light piston. The surrounding air has a temperature Ts and the atmospheric pressure is Pa. Heat may be conducted between the surrounding and the gas through the bottom of a cylinder. The bottom has a surface area A, thickness x, and thermal conductivity is K. Now, assuming all changes to be slow, find the distance moved by the piston in time t. Let's say this is my cylinder and this is my base. The base is having an area of cross section A and thickness is x. Through this, heat can come out or come in. This is my piston. Let's say it moves a distance L downward that we have to calculate. Fine. So the thing is that heat transaction is taking place through the bottom surface. Now let initial temperature of the cylinder is T0, but one thing is pretty clear, that since the Q is changeable, so the temperature won't be a constant. So let's say at any instant of time, I have dq by dt, that is the energy or the heat flowing through the base, given by K into area into, let's say at any instant the temperature of the cylinder is T, so it will be Ts minus T divided by X. Alright, now this Q, we know that Q is given by NCP delta T, fine, or the change in temperature. So I can write dq by dt as NCP dt by small dt. Okay, so I do have N. The value of Cp is 5 by 2R, because for a monoatomic gas the value of Cp is 5R by 2. That is for the monoatomic. It is given that the gas is monoatomic. Fine. So it is equals to dt by small dt is equals to Ka Ts minus T by X. So just rearranging this equation, I have dt is equals to Ts minus T and Ka by X into 2 by 5R with N dt. So let's say time varies from 0 to T, and by the time the temperature of the gas varies from T0 to, let's say, any temperature T. So I do have natural log of Ts minus T with a negative sign out there is equals to Ka by X into 2 by 5 Rn T, and the limit value goes from T0 to T. So on solving this, I get Ts minus T0 or Ts minus T divided by Ts minus T0 is equal to minus of Ka X into 2 by 5 Rn into T. Okay, so now solving this equation for the value of T, I have Ts minus T is equal to Ts minus T0 times of e to the power minus Ka 2 by 5x Rn times of T. Okay, so the value of T from here comes out to be Ts minus T0 into e to the power minus Ka 2 5x Rn T. Alright, now I'll subtract minus T0 from both sides, so it can be written as T minus T0, that is the change in temperature, is equals to Ts minus T0 minus Ts minus T0 into e to the power minus 2 Ka by 5x Rn. So delta T comes out to be Ts minus T0 taken as constant 1 minus e to the power minus 2 Ka T by 5x Rn. Alright, this is my delta T. Now the external pressure is constant PA. So what happens is that we can write PdV, that is atmospheric pressure, into change in volume is equal to number of moles into real gas constant into the change in temperature. Okay, because external pressure is constant. So PA into change in volume is A. Let's say it comes down by a length of L. So change in volume will be AL is equal to NR and delta T. So the delta T value is PA into AL by NR. I'll substitute this delta T value over here. So I get PA AL by NR is equal to this big expression. So the value of L from here comes out to be NR by PA into atmospheric pressure into this very big expression, that is Ts minus T naught into 1 minus e to the power minus 2 kAt by 5x Rn. That is my answer.